So how would the mathematicians write this using m?
M over 2.
Now, and actually, I guess if we did the math, it wouldn't really be m over 2. Yeah, and actually, we'll get more intuition. We could put these into one fraction, but we'll get more intuition if we write it like this. So we'll write it like this. And now m could still start at 0, right? 0 is the very first case up here. So this is still a case where m could be 0 or 1 or 2 or any whole number. So this is our formula. If two waves are starting in phase, when will they end out of phase, completely out of phase, 180 degree, when their path length difference is a whole number of wavelengths plus an extra half wavelength to get them out of phase. And then when will they end in phase, when the path length difference is just a whole number of wavelengths. Okay, I think that in your course this is going to be used a lot more often, but this is in the book too, and this is good to know. So. Okay, so those are our two formulas for that. So what does this m stand for again? Well, it's kind of standing for how many complete wavelengths we're adding to the distances here. Here they start out, the first time they're out of phase is when there's a half wavelength difference, and then you keep adding m number of complete whole wavelengths. And here m is easier to interpret. It's just the number of wavelengths difference there is in the path. So again, the key thing is the path length difference. Okay? Okay. All right, so now we know when waves will be in phase or out of phase, and now we can see what happens when two waves come together at the same point. So let's see what happens when two waves come together at the same point on a screen. So here's our screen. And let's say that we've got wave A coming in, and wave B coming in. And let's say they're both coming into the same point on the screen. So kind of naturally, you would kind of expect there to be a bright dot at this point. If we have two waves of light, both focused on the screen at this point, we would expect to see a bright dot there. Or if this is some kind of light meter, a light detecting device, you would expect it to go ping because it feels the light hitting it. But if it's just a screen, you would expect to see the light. But let's think about that a little bit more carefully. The subtlety here is we have to decide, are the two waves going to be coming together when they're in phase or out of phase? And now here we get to interference. So let's say that they're in phase. Well, if the two waves are in phase when they hit the screen, now we're not talking about the start anymore, we're talking about the end. If they're in phase when they get to the screen, are we going to have constructive or destructive interference?
Constructive.
Yeah. This is what's called constructive interference. We'll just take the simple case where they're completely in phase, so we get complete constructive interference. Is that going to give us an especially bright spot or an especially dim spot? Okay, so we're going to get a bright spot. So we see a very bright spot on the screen here, or our light detector would give a really loud ping. The way that looks like is here's two waves that are in phase. Remember that this distance is what we call the amplitude. The distance from equilibrium to crest or from equilibrium to trough is what we call the amplitude. So let's assume these both have the same amplitude. Generally in this chapter we can assume all the light is the same type of light with the same wavelength and amplitude. The only difference possibly between the two light waves might be that they're in phase or out of phase. Otherwise we'll assume they're the same. So is this distance the amplitude? No, that's twice the amplitude. So the amplitude is not from crest to trough. It's from crest to equilibrium or from equilibrium to trough. That's a common mistake. I think we've seen that before. All right, so what's the combined wave going to look like here? If these two waves both hit the screen at the same point, kind of how would we draw the combined wave?
It's just like the amplitude is double.
I'm sorry?
The amplitude is double?
Yeah, the amplitude will just be double. Because anywhere that they're both cresting, the two crests add together, and where they're cresting. So for example, this crest might be +5, and this crest might be +5. Well, +5 and +5 is +10. And this trough would then be -5. Well, -5 and -5 is -10. So I guess that the overall thing, if I could draw well, this would be what they would look like if they had about twice the amplitude as before. Okay, so now we have about twice the amplitude. So I should say the new amplitude is about twice what the old amplitude was, or it should be exactly twice if these have the same amplitude. And how would we see that psychologically? Well, it would seem like a bright spot. The amplitude, the higher the amplitude, the brighter the spot seems. The amplitude is an indication of the brightness. So if we give a wave a higher amplitude, how would we notice that psychologically? Well, we would see it get brighter, right? Well, we should also review what happens if you change the wavelength of light. How do you psychologically perceive that?
The color.
Yeah, remember the wavelength is like the color. How about if you change the frequency? How would you psychologically perceive that?
Is it also the color?
Yeah, good. Kind of a trick question. But remember, because of this equation, you can't change the wavelength without changing the frequency, because the speed stays constant. So both frequency and wavelength are indicating the color. Remember we saw that table in your book where they had all the different types of electromagnetic radiation ranged, and on the top they had the wavelength axis, and on the bottom they had the frequency axis, which shows that frequency and wavelength are two sides of the same thing. All right, well, we're assuming here we have two waves of the same wavelength. That means same color. We're going to be assuming we're working with, at least at the start here, we're working with monochromatic light. Okay. Now suppose that they are 180 degrees out of phase when they hit the screen. What can you say about what's going to happen then?
Destructive.
Yep. Now they'll have complete destructive interference. And what will we see on the screen?
Either like a dim spot or...
Yeah, either a dim spot, or if they really have the same amplitude, there'll be nothing. Because if they really have the same amplitude, they'll exactly cancel each other. And that's what we're going to be assuming. So basically, we'll see nothing at this point. No spot, or maybe a dark spot, we could say. Alright, so the pictures aren't that good again, but can you see, hopefully I was trying to draw these as being 180 degrees out of phase. When this one is cresting, this one is troughing, and when this is troughing, this is cresting. And if they had the same amplitude, well, then this point would be +5, and this point would be -5. And +5 plus -5 is 0. And this would be -5, and this would be +5. And +5 and -5 is 0. So what would the combined wave look like? The combined wave would just be at 0 all the time. Okay, so if the two waves really have the same amplitude, we get complete destructive interference here, and there's no spot at all. And if we were approximately at this point, at least we would have a dark spot. Okay. And by the way, remember, we now know how to decide when they're going to be in phase and out of phase. It depends on the path length difference that they've traveled. Because again, we're always assuming that they started in phase. At the beginning of the experiment, we're assuming they started in phase. Well, if the path length difference is a whole number of wavelengths, we know that they're going to end up in phase, and we're going to get a bright spot. But if the path length, I erased the formula, but if the path length difference is half a wavelength plus a whole number of wavelengths, then they would be out of phase, and we get a dark spot.